Okay. The next four exercises are about finding formulas for some functions. So in this ninth one, we are given an equilateral triangle whose side length is x. We have to find its area and its perimeter in terms of its side length. In other words, we have to find these variables, that is area and perimeter, as functions of the side length. So let us start the solution by drawing an equilateral triangle, which we will not draw a geometrically accurate equilateral triangle, just one that's enough for our purposes. So you can assume that this is an equilateral triangle whose side length is x. ABC as shown in the adjacent figure B an equilateral triangle whose side length is x. Okay. Now what we do, we draw a perpendicular from the vertex A to the side BC and let that perpendicular meet BC at the point D, or let D be the foot of the perpendicular. Draw a perpendicular from vertex A to side BC, which meets BC at the point D. Okay. Now it's given that the side length is x, so that means BC equals x, and we know that since the triangle is an equilateral triangle, so this perpendicular bisects BC, that is BD is 1/2 of x. Since we can in fact write like this, since is equilateral, we know that D is the midpoint of BC. Hence, Okay, now just like BC has length x, AB also has length x. And BD is BC divided by 2 because T is the midpoint of BC, and that is x by 2. Now from the right angled triangle ABD, where of course this is the right angle, we use Pythagoras theorem to have this. We can write at once, but anyway, let us just first write the Pythagoras theorem. The square of the hypotenuse equals the square of the other two sides. Thus, BD, we know BD, we don't know AD. So AD square is AB square minus BD square. That means x square minus x by 2 whole square, which is x square minus x square divided by 4, and that is 3x square divided by 4. Or because AD is a length, so AD cannot be negative, so AD is this. Now we can find the area of the triangle using the usual area formula for a triangle that we get from geometry, which is 1/2 of length of base times length of altitude. Thus, the area of triangle ABC is 1/2 of AD times BC. Now we have already calculated AD times x, and BC is x, so this is equal to square root of 3 divided by 4 times x square. So this is the area of an equilateral triangle as a function of its side length. You know the side length. Using this formula you can find the area of the corresponding equilateral triangle. And the other thing, the perimeter is of course very trivial, and because the perimeter is the sum of the side lengths, perimeter of triangle ABC is 3x, because all the sides are of equal length and each one of them is of length x, so the perimeter is 3x. Then exercise 10. Express the side length of a square. It will be a little difficult to clean the board today because yesterday it rained, so the humidity has gone up. Express the side length of a square. As a function of the length d. Length d of the square's diagonal. Then there is more. Express the area as a function of the diagonal length. Ink is needed. Okay, so this time we have a square. Okay, so let's draw a square as best as we can. Fine. Now what is given? Side length is to be expressed as a function of the length of the square's diagonal. Okay, so diagonal length is given. And since it's a square, both the diagonals are of the same length. So this length is given and it is d. AC is d and BD is also d. Let ABCD be a square as shown in the adjacent figure. Whose diagonals are of length D. Join the vertices A and C so that we get the diagonal AC. Okay, now for the sake of our calculation, we are going to give some name to the side length of the square. Let the square have side length x. Now AC is D and AB and BC are both x. So from the right angled triangle ABC, this is the right angle of course, we get AB square plus BC square equal to AC square, or x square plus x square is equal to D square, or shall I write it, shall I write the final quantity, or let's just show all the steps. 2x squared is equal to D square, or x is equal to D divided by root 2. So we have expressed the side length x in terms of the diagonal length. It is D divided by root 2. And you can see that since square root of 2 is greater than 1, so the side length naturally is less than the diagonal length. Okay. Now we have to express the area also as a function of the diagonal length. Since we have got the side length, so area is square of that. So we can use this expression. Thus, area of the square is x square, which is equal to d square divided by 2. So that means the area is half of the square of the diagonal length. So this completes the solution. Next, express the edge length of a cube as a function of the cube's diagonal length d. Then express the surface area and volume of the cube. As functions of the diagonal length. Okay, since a cube is a three-dimensional object, so we have to draw it carefully, and we cannot actually draw it because it's 3D, but we can draw a 2D representation of it, the way we usually draw a cube on a two-dimensional surface. Okay, so let us first draw the thing. It will be better if we use this entire place to draw it. Okay, so luckily I seem to have chosen some length that can be measured. 1, 2, 3, 4, 5, 6, 7. Okay. The rest we can just simply draw parallelly. We can adjust the figure. Have I taken this one also? No, I think this will be longer. 2, 3, 4, 5, 6, yes, 7. The rest actually cannot be seen from this side, but we will have to draw, so we will use dashed line. I have made some sort of mistake, but you can understand what we are doing here. I mean, we have not, you don't have to be 100% accurate in our drawing. This part you can understand, they meet. Okay, so the dashed lines are behind this object. I mean, it's not on our side. Now, when we say diagonal, okay, but before we do anything, let us name the vertices. Since we will be dealing with, okay, anyway, what's there in name? A, B, C, D. This is this face that is on our side, and the other vertices that belong to the other face that is on the other side, let's name them E, F, G, H. Okay, so we can write like this. Consider the cube drawn above. Now, when we say diagonal of a cube, such a diagonal does not lie on any of the faces or on any of the surfaces of the cube. For example, one diagonal, all the diagonals of course will have the same length. One of the diagonals, for example, okay, let me just say, or let me just make it clear when I say that a diagonal will not lie on any face. It means AC is not a diagonal, but AG is. And the reason we are using a dashed line, it's because AG will be lying inside the cube. Okay, that's why we are using a dashed line. In particular, this diagonal AG will be on the other side of this face, this square face ABCD. So that's why we are using dashed line. So this is a diagonal, but its length cannot be immediately understood just by joining A and G. We also need to join A and F. This line segment AF is not a diagonal of the cube, but it's a diagonal of the square face, that is the bottom face ABFE. Okay, we join consider the cube drawn above means also consider the names we have given to the vertices. We join A and G and also A and F. Are we given anything like diagonal length D is given, and we have to express the edge length in terms of the diagonal length, right? Okay, let the edge length of the cube be x. Okay, now first of all, we measure the length of AF in terms of edge length x. Note carefully that the bottom square ABFE, in that square we consider this triangle ABF. This is actually a right angle triangle where this is the right angle. So we write from the right angled triangle ABF we can write at once, because here we want to find AF, which is actually the hypotenuse of the triangle. So AF is equal to square root of AB square plus BF square. So this is, since side length is x, AB is a side, BF is also a side, so x square plus x square. So we get the side, the length of AB as square root of 2 times x. Okay. Now we consider another right angled triangle which itself is vertical, namely AFG, this one, where this is the right angle. Thus, from the right angle triangle AFG, we get, so here AG is the hypotenuse. AG square is equal to AF square plus FG square. Now AG is the diagonal of the cube whose length is given to be D. Thus D square is equal to AF square. We have already found AF, square root of 2 times x. So this is 2x square plus FG square. FG is a side of the cube, so that is x square, or d square is equal to 3x square. So our aim is to find the side length, edge length or side length, same thing, as a function of cube's diagonal length. So it is this edge length as a function of diagonal length. You get the edge length when you divide the diagonal length by square root of 3. Thus the volume of the cube is the cube of its edge length, and that is d cube divided by cube of square root of 3, which is 3 root 3. Root 3 square times root 3, so 3 root 3. And the surface area okay. How many surfaces are there? Each surface is a square, or each surface means each face is a square. So 1, this ABCD, that opposite face 2, this face 3, its opposite face 4, the bottom face 5, and the top face 6. And each one is a square, means each one's area is x square. So 6 of them is 6x square. So this is 6 times d square divided by 3. So that is 2d square. So the volume is this in terms or as a function of diagonal length, and surface area is this again as a function of diagonal length. D square divided by square root of, have I got it right? This one is okay. When we square this, we of course get d square divided by 3, and it's 6 times that, so 2d square, yes. Next, there is another one. A point P in the first quadrant lies on the graph of this function express the coordinates of P as functions of the slope as functions of the slope joining P to the origin. We can draw a figure in this case also. We can roughly draw the graph of this function. Actually, we should draw figures whenever we are trying to do something and we can draw something. Even if it's only a representation of the actual thing, or it's not the actual, for example, the cube that we drew. If you just think of it, the drawing that we had there is not actually a cube but a 2D representation of it, but it's very useful if we have something to look at, then things become much more clear. Okay, now the graph of this is roughly like this. Okay, it goes on that side indefinitely without any bound. However, it stops here. It's part of a parabola, which the other part we don't have, because f of x is positive square root of x, not at the same time negative. I mean, that is not part of this function. So this is the graph. Now P is any point on this graph whose coordinates are of course some coordinates x and y. And now if we join P and the origin, we get this line. From the look of the graph, you can see that as P approaches the origin, the slope of this line increases, and in fact at the point 0 the slope becomes infinite. So, and that also does not make sense if you, instead of thinking of slope, you just think of the situation when P coincides with the origin, then the line has 0 length which joins P and the origin. So such a line, for such a line, slope is not defined. So we have to avoid the case where P coincides with the origin. So this, if you want, you can write this. So in fact this y is nothing but square root of x. Okay, since P is a point on the graph of fx equal to square root of x, the coordinates of P are x comma square root of x, where we also have to mention that x is a non-negative real number. X cannot be negative. Okay. For any such point P, capital P, for any such point capital P different from the origin O, the slope M of the line joining P and O is M equal to we have to find the slope of a line that passes through these 2 points, for which we already have a formula. Difference of the y coordinates divided by difference of the x coordinates. From this formula itself you can see why we need P to be different from the origin, because if x is 0 then this ratio becomes or this quotient becomes meaningless. So this is equal to 1 over square root of x. This implies so x will be 1 over m square. 1 over m is square root of x, so x, yes. Thus the coordinates of P as functions of the slope M of PO means the line PO, are x is 1 over m square and square root of x, that is the y coordinate, positive square root of x. So 1 over m. How are we able to cancel square and square root and write m and not absolute value of m? That's because you can see that m itself is positive, because the line is like this. I mean, these lines all have positive slope, no matter wherever p is on this curve, except for the position 0. Elsewhere, wherever p is, the slope will change, but it will stay positive. For negative slope, the line should be like this. And for a vertical line, of course, slope is not defined. So this is the x coordinate in terms of slope, and this is the y coordinate in terms of slope. So because of positivity of m, when we take square root to calculate the y coordinate, square root of x, then we get 1 over m. So this is the solution. Okay, then we come to some other types of exercises. Functions and graphs. Graph the functions in exercises 13 through 24. What symmetries, if any, do these graphs have? Use the graphs in figure 28. These graphs you can find in the text or in one of the previous videos where we actually roughly showed the graphs of some particular functions for guidance. As needed. Okay, so these are the functions. Now what I'm going to do, I'm going to draw the rough shape of the graph. Of course, I'm not going to make tables and actually draw the graphs here. We can do that, but it will take an awful lot of time, and it's not necessary also. You are being asked to draw the graphs for yourselves using either of these two things. You take a graph paper, make a table, plot some points, and then join them and figure out the graph. Or you can, if you are feeling somewhat lazy, you can search this on Google, Desmos graphing calculator. You click on the first link that you see, it will take you to a web page which is an online graphing facility. You visit that page and you will see that you can in fact draw any type of graphs of not just functions but equations, relations, inequalities also. But it will be a nice exercise to draw at least one or two graphs on your own without taking the help of any sort of graphing machine. So these are the functions. The function is this, y equal to minus x cube. So if you recall, we already know the graph of y equal to x cube. So this is just the negative of that. From that itself, from the graph of the cube function, you can figure out the graph of this function based on the way this formula has been given, that is, there is only a minus. So previously, for a given value of x, the cube value that you got, this time it's the negative of that. So it will be reflected on the x-axis because the value is negative, and accordingly the graph will look like this roughly. So because these are just some rough shapes of the graphs and not the actual graphs, I am not going to write solution. This is the x-axis, this is the y-axis. Originally our x cube graph goes like this, so it will be the opposite. It will be like this. Which of course I haven't been able to draw quite nicely, but you can understand what we are doing here. In exercise 14, the function is this, minus 1 over x square. And also one more thing, you have to figure out if the graph has any symmetry. We have already discussed about the types of symmetries that a graph can have. Either it can be symmetric about the x-axis, or symmetric about the y-axis, or symmetric about the origin, those type of things. Okay, so that also I am not going to say. So y equal to minus 1 over x square. Here the graph will look like this. Some things about these graphs you can almost immediately see from the formula for the function. For example, in this case, you cannot put x equal to 0. So here the graph has two parts. It's not in one piece. Okay, and that is because no part of this graph, it's broken into two parts, can touch the y-axis because of the lack of the point x equal to 0 in the domain of this function. Then exercise 15. 15 is y equal to minus 1 over x. Here also x equal to 0 is not a point in the domain of the function. Here also the graph is broken into two disconnected parts. You can figure out this graph from the graph of y equal to 1 over x. In fact, actually that's how one should figure out the graph. Not always blindly by first creating a table, plotting the point and mechanically joining those plotted points as nicely as one can and getting the graph. Not always following that path. You are actually supposed to figure out this graph from the graph of this function y equal to 1 over x. In that case, this is the graph. That also has two disconnected parts. Now, because if you put one input from here into the function, this function, not the one that is given here, 1 over x, then your output is here somewhere. Now the output is having that same numerical value but is negative. So it instead of here, it will be here at an equal distance. So that's why this half of the graph gets flipped about the x-axis, as if x-axis is a mirror. So instead of this, you get this. Similarly, instead of this, that also gets flipped about the x-axis and you get this. Okay, so that's how you have to argue with yourself to figure out the graph. But then of course, if you actually want to draw the graph, you need a table or some sort of graphing calculator. Minus 1 over x. Then, okay, next 16. One over absolute value of x. This also can be, one can figure this out from the graph of 1 over x. In this case, even when x is negative, you will get positive values. So this part of course will stay just as it is. This part gets flipped. So here the graph looks like this. because we don't have a negative y value, and note from the formula of this function that we also don't have a 0 y value. That's why none of these two halves of the graph will ever touch the x-axis, although the further you go from the origin, on either side of the origin, the closer this graph will get to the x-axis without ever touching the x-axis. And then 17, y equal to square root of absolute value of x. If we had simply x here, we would be forced to remove the negative part of the x-axis, because then we will not be able to put negative values of x. But now we can, and that's why, unlike the graph of just simply square root of x, this one has its parts on both sides of the origin, or rather more specifically on both sides of the y-axis. And also from the formula itself we can see that the value of y is never negative, so no part of the graph goes below the x-axis. And in this case, this is the graph. One half of course looks just like our ordinary graph. Actually, the curve has to meet the y-axis in such a way that the y-axis becomes a tangent to this curve at the origin. So it starts vertically, but just after that it deviates. At this point 0, the tangent to the curve is y-axis, but the moment you go a little on this side or a little on that side from 0, from the origin, the tangent tilts. Okay, it's no longer vertical. And the other half is just its mirror image. Okay, so that's how the graph will look. And then 18. The 18th one is y equal to square root of minus x. So here x cannot be positive. It can be 0 and it can be negative. But y is positive, keep that in mind. So in this case, this half is not there. We have this half. That is the graph. And one more thing, these drawings I am doing freehand now. It does not go like this. This height, it keeps on increasing without any bound. that means this graph does not come back down, it goes higher and higher. Then 19 is something else entirely. This is y equal to x cube divided by 8. That means it's just the cube function, but now the values are getting diminished because we are dividing every cube value by 8. And the graph will look like the graph of y equal to x cube, but the way it curves, the points through which it passes, those things will change. So x cube graph is like this. This one will also be like that. The shape will not change. But it will be somewhat a little wider than the previous one. Why, that I leave to you to think. Okay. Y equal to x cube will be like this. Do you see? Okay, let me just say a little bit about y. Say y equal to x cube will be like this. When we are dividing by 8, why is it getting wider? It's because previously this is y equal to x cube curve and this is y equal to x cube by 8 curve. If you choose some particular value of x, previously this was your x cube, this much was x cube, but now it is being brought down by division by 8. So now this is your x cube by 8. Okay, and this of course will happen if x is greater than 1. If x is less than 1, then the role gets reversed. I mean, you can figure out what is going on here. The original graph was like this. This is a bit wider. Four more. The 20th one is y equal to minus 4 root x. Okay, so because we have root x, so only non-negative values of x are allowed. So the graph will lie on to the right of the y-axis. But because negative of this, I mean all these values are non-positive, so the graph will lie below the x-axis also at the same time. So it looks like this. And besides all these things, it's also multiplied by 4. X, y, this of course is the origin, and the graph, it goes down like this and it keeps going down. Then 21. y equal to minus x to the power 3 by 2, and its graph will also lie below the x-axis. Do you see that even before drawing the graph, we can in fact, just by looking at the formula, know one or two things about the graph. For example, here, as I was saying, because we have square root of x, so only non-negative values of x are allowed. So the graph lies on this part of the y-axis. Also, because of the presence of this minus sign, all the values are none of the values is positive. Either it is 0, for example here, when you put x equal to 0, you get y equal to 0. For positive values of x, the values of y are negative. So the graph lies below x-axis. Here also, same thing. The graph lies in the fourth quadrant. Here also you have a square root because of this 2. This is in fact square root of x cube, or cube of square root of x, also same thing, and we have minus sign. But unlike this one, in this case the graph goes like this. It also goes down, but it goes like this. Then 22. The 22nd one is minus x to the power 3 by 2. Okay, in this case, okay, you see, now we have square root of minus x. So x now cannot be positive. X either is 0 or it has to be negative, so that the number minus x is non-negative. So the graph will lie to the left of the y-axis, and it's like this. It looks like the graph of y equal to x square, but there are differences. It will pass through its own points through which it is supposed to pass. And then 23. The 23rd one is y equal to minus x to the power, in place of 3 by 2, now we have 2 divided by 3. And here you see, now we don't have square root, we have cube root, and when we have cube root, there is no restriction on x. Every real value of x can be put as input in this function. So the graph will lie on both sides of the y-axis, and the graph looks like this. X, y, and it goes like this. Here also this goes up, higher and higher. On this side also same behavior. And finally 24. In this case it is minus x to the power 2 by 3, here the graph is obtained by, no, I should not say obtained by flipping this, but can we say that? No. Anyway, the graph looks like this. And these are all the functions and their graphs, those type of exercises. And then we have exercise 25. Graph the following equations and explain why they are not graphs. Of functions of x. There are two equations are given. This, and in part B we have y square equal to x square. So let us draw the graphs. The equations that are given are simple enough for us to actually draw the graphs without even making tables. Okay. Now let's first draw the axis and then we will see. For a given value of x, we can of course, oh but wait, we cannot put any value of x because x has to be the absolute value of something. So x cannot be negative, x can either be 0 or positive. Now when we put x equal to say 0, there is only one possibility for y, that is 0. And when we put some positive value of x, correspondingly y has two values. One of them is x itself and the other one is minus x. So the graph of this equation will look like this. So only positive, non-negative values of x are allowed, and for a given value of x we have two values of y. One of them is x, that is if this is our x for example, then this point is x comma x and this point is x comma minus x. So those two values of y, x and minus x, can be put here. Both of them will give you x because x is positive. So one half of the graph is this part of this line y equal to x and the other half is y equal to minus x. Okay, let's draw the other graph also and then we will see why they are not functions of, graphs of functions of x. This equation is equivalent to what? Y square minus x square equal to 0 or y plus x times y minus x equal to 0 or y is equal to x and y equal to minus x. So the graphs, or rather the single graph in this case is the pair of these straight lines. That one, pair of these two straight lines. Now we can see that these graphs, this is one graph and this is another graph. None of them can be the graph of any function of x because both of them fail the vertical line test. So you can just simply write like that, since both, in fact let's write that line here. The graphs in part A and part B are not graphs of any functions of x because they fail the vertical line test. That is the reason. Except at the point x equal to 0, any other value of x you take, any other permissible value, you cannot take some value of x here. In this case you have to take a positive value of x if you are ignoring the point x equal to 0. For any such value there are two values of y, so vertical line test fails. In this case also same situation. Okay, next 26 is also something similar, but anyway, let us see it. Graph the following equations and explain why they are not graphs of functions of x. In this case, the equations are these. The first one we have already encountered, although not as an equation but rather as an inequality. Okay. So let's draw the graphs. From what we already saw before about this, the first one, we can, without saying anything much, we are just going to draw the graph. Previously, we drew the graph of this inequality. Okay, now in its place we have equation. So if one argues similarly, like what we did back then one gets this graph. This is the x-axis, this is the y-axis, and say these are the points at distance 1 unit from the origin and on the axis. Join these points to draw the square. These coordinates will make this thing absolute. I mean, we will know exactly what we have drawn. 0, 1, minus 1, 0. Just give me a moment. Now, previously when we drew the graph of this inequality, we got this diamond shaped region, which actually is just a square. But region means the points that represent this inequality are all the points on this square and inside this square. Now we don't have inequality, we have equation. So now the graph is the set of all points on this square, not inside the square. Okay. And this is not the graph of a function. Again, same reason, vertical line test fails, except at these 2 points. For other values of x, I mean, except for x equal to -1 and 1, for other permissible values of x, there are for each one of them there are two values of y. So this is not a graph. And what about this one? This is quite easy to figure out. X plus y is either 1 or minus 1. So it's a pair of these two straight lines. So we just have to draw those two straight lines. And because the equation is at once representing two straight lines, so both the straight lines collectively form the graph. Okay, not any one of them at a time. Together they form the graph. So it's also a broken one with two disconnected parts. So x plus y equal to 1 is just this line. This is also 1. It's this straight line. Passing through these 2 points, one of them is 0, 1 and the other one is 1, 0. Because if you put x equal to 1 and y equal to 0, you get 1, and also when x equal to 0 and y equal to 1. What about this one? If you put say x equal to 0, then y is minus 1. So it will pass through this point 0, minus 1. And if you put y equal to 0, then x is equal to minus 1. So that means this one. So it will pass through these 2 points. And also from the way these two equations look, you can see that they represent parallel lines. So these two straight lines together form the graph of this equation. Here also this graph cannot be the graph of any function of x because it fails the vertical line test everywhere. Not like here, for example, at x equal to 1 and x equal to minus 1, there are in each such case there is only one value of y. Here for every value of x there are two values of y. So the vertical line test fails everywhere. So this is also not the graph of a function of x. So that's the solution. So let us end the video here itself. After this we have the other notions that we have come across in this chapter, that is even and odd functions, sums, differences, products and quotients of functions, and also after that we will see composition of functions and some other things. So that will be all for today. You are free to write in the comment section about what you feel about this video. So that's it. Tomorrow, what do we have tomorrow? Analysis. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.